Hi, and welcome to TEMEKO. In this video, we will take a look at what is meant by a distributed loading and how to reduce it by determining an equivalent force resultant, which has the same external effect as the distributed load. During the process, we will learn how to define the magnitude and the location of this resultant force. Let us get started. Before we can determine the equivalent force resultant for the distributed loading, we have to first know what a distributed load is. A distributed load is one kind of load which is distributed across the whole region of an element that can be, for example, a simple beam. Think about the case in which there is a beam and on top of it is a line of sandbags. Here, the weight of the sandbags is distributed over the beam, and the intensity of this weight at each point of the beam surface is defined as the pressure P, which is also called force per unit area. Most of you may already know this, but for those who want to recall this, the unit of pressure P is pascals, and its abbreviation is PA, which can also be written as Newton per meter square. Note that in our beam case, because the pressure load is not uniform along the length of the beam, we need to describe the pressure load by using the function P equals Px. If we multiply it with the width B of the beam, then we can obtain the loading function Wx, which is a measure of the load distribution along the length of the beam, and it is measured as a force per unit length. Next, we are going to discuss how to simplify a distributed loading into a single resultant force. Normally, if we want to determine the magnitude of a distributed load, the easiest way would be to reduce it to a single resultant force. We can determine the equivalent resultant force by using an integration, because a distributed load is formed by an infinite number of parallel forces dF acting along the length of the structure. The equation from which you can determine the resultant force can be written as follows. Fr equals integral over L of Wx dx, which equals integral over A of dA, which equals A, where A is the total area under the load function Wx. You can also define the location of the resultant force, but for this purpose you have to determine the moments of the force resultant and the force distribution about point O. If we consider differential element dx and the applied distributed force dF, then a differential moment about point O, which is produced by dF, can be written as follows. MO equals x times dF equals x times Wx times dx, where x is the distance between point O and force dF. The whole moment of the point O can likewise be determined as follows. Summation of MO equals integral over L of x times Wx times dx. On the other hand, the resultant moment, which is equal to the total moment about point O, can be determined by using the resultant force Fr and the location x bar, which is the distance between point O and the resultant force. This leads to the following resultant moment equation. MRO equals x bar times Fr equals x bar times integral over L of Wx times dx. Now that we have defined both moment equations, we can solve the resultant force location x bar by setting the equations as equal to each other. Solving for x bar, this leads to the following equation. X bar equals integral over L of x times Wx times dx divided by integral over L of Wx times dx. You should keep in mind that in addition to telling us the location of the resultant force, x bar also represents the geometric center coordinate under the distributed loading diagram Wx. Therefore, the line of action of the resultant force is on the same line with the point C, which is the centroid of the area and the focus point of the load. Hopefully, after watching this video, you know the definition of a distributed loading. You know how to reduce the distributed loading into a single resultant force, and you can also determine the magnitude and the location of this resultant force. Thanks for watching and have a nice day.